So Einstein summation notation, I'm just going to walk through these notes, and you guys please stop me if you have any questions, and please ask. So this is basically a way of simplifying the way we write out vectors and vector components, and you'll actually see it's quite powerful. So, we often write a vector, say vector A, we write it as AXI hat plus AYJ hat plus AZK hat, right? We might also write it in this third form here, where we say A1, E1, A2, E2, A3, E3. And what our understanding here is that this E1 is often something like X hat, but it doesn't have to be. The only restrictions on E1, E2, and E3 is that they be orthonormal vectors. What does orthonormal mean? It means that the dot product of any of them with themselves is 1, that is, they're normalized to 1. And the orthogonal means that anytime you take the dot product of 2 of them that are not the same, you get 0. Right? And hopefully we've all seen this a lot, in past, like x hat, dot x hat is 1, I dot j, j dot k, I dot k, those are all 0. Is there anyone, Carter, Kate, Kieran, you're all familiar with that, right? Okay. And so, when I write out a vector, when I say vector A, right, sometimes we just write it as like these components, A1, A2, A3. Sometimes we write it in this way, sometimes we write it in this way, whatever. Physicists often get rid of the I, J, and K. We write X, Y, and Z. And you're actually going to see a little bit of why we do that in this discussion, that we use I and J for other things. Plus, we just find that interest students have too many things going on to keep track of, so. So the first thing is, if I just say like A sub I, what is that? Well, it's just a number, okay? If I had a vector A that was 3, 4, and 8, 3, 4, 8 like this, and I said A sub 2, that would mean 4, okay? But what's really important to keep track of through this conversation is when I say A sub I simply mean a number. I don't mean A1, E1. I mean the number that you multiply the unit vector by, all right? So A sub I will simply mean one number. And we're going to then learn that things that have one index are called vectors. So anytime you have one index or one indice, right, that is a vector. Okay. Another thing that these are called are scalars and C numbers. C number stands for commuting numbers, okay? There are numbers that do not commute, although probably none of you have ever heard of them. Grassmann numbers are an example, which unless you go into quantum field theory research, look at supergravity, things like that, you probably will never encounter Grassmann numbers. But there are numbers that do not commute. So, okay. So let's imagine, again, I have that vector 3, 4, and 8, and A2 would be 4. All right. So what we're going to do now is add, we're going to go back and do something that should be really easy, and we're going to make it look really hard. And that is, I'll take vector A, which can be written as the following sum. That is A sub I, E sub I, sum from -1 to 3. And we write that out. We get A1, E1, A2, E2, A3, E3. Now, unlike A sub I, E sub I is no longer a number. Okay? Does that make sense to you, Kate? Like because I write this hat on top of it because I'm denoting that it is a vector still, whereas this doesn't have the hat, it's not a vector. So while this only has a single index, this means E1, I could take to be X hat, right? And E2, I could take to be, Y hat. And E3, I could take to be Z hat. Okay. So now if I want to do the dot product of two vectors A dot B, you probably know that already. It's just AX, BX plus AY, BY plus AZ, BZ, right? But again, we're going to make it look more complicated because we're going to learn something from this. So using this way of writing the vector here, we're going to now construct the dot product of A and B. Okay, so we are going to write one sum over I for A, and we're going to write our next sum over J because we don't want to confuse anything. If we want to call this I and I, you might think that I had something to do with this I, and they don't. So we just go to the next letter of the alphabet, we call it J. Any questions before I move on? Carter, you good with this stuff? Great. Kate, you're good? Okay. All right, great. So then what we're going to do is, we've still got our dot here, and we're now going to pull all of our sums out front, and hopefully remember from Calculus 2 that we can always rearrange the order of finite sums, that any finite sum will always add up to the same number. It is only infinite sums that change their value when you change their summation order. So, and we will then rewrite this sum as the following. So we get a sub I bj, and then e sub I dotted with e sub j. All right? And then we sort of mentioned this above. What do you get when I equals j? You get 1. Right? So if you have x hat dot x hat, you get 1. If you have y hat dot y hat, you get 1, etc. If you have x hat dot y hat, however, you get none. Right? So it's a pretty important point I want to make sure that we're clear about here. That is, if I does not equal j, you're going to get a 0. Okay? And so this is actually going to cause us to introduce, there's that noise. Is your fan just turned on, Kate? Okay. It's possible that I have intermittent relapsing insanity, and that's okay. So we're going to introduce a new function called the Chronicle delta function. That's just delta ij. Okay, and delta ij is going to basically be defined as what you get when you take the dot product of e sub I and j sub I. Okay, or e sub I, e sub j. And again, what are you going to get there? You're going to get a 1 if I equals j, and you're going to get none if I doesn't equal j. All right. So now we have something that has two components to it, I and j. Right. However, this is still just a number. Right. It is what we call a C number, meaning it commutes with any other number. All right. But now the question is, where does that number come from? All right. So we'll get back to that in just a minute, but this first thing that we have that now has two indices instead of just one. All right. So we're now going to replace e sub I, e sub j with delta ij. Okay, so we'll put that back in. And what do we get here? We have these sums that are sloppily written. I apologize for that. I 1 to 3. And now we've replaced the e dot j with the delta ij. All right. So now what we're going to do is we're actually going to perform the sum over j. Meaning that we're going to get, right, this term here, when I sum over j, is going to give me 3 terms. It's going to give me b1 delta I1. It's going to give me b2 delta I2, and it's going to give me b3 delta I3. Okay. And so that looks like, you might say, aren't we just doing a dot product? Why is this so hard? Well, we'll hopefully see why in a minute. But now you have 3 terms that came out of doing that j sum. But do we really have 3 terms? What's going to be true here? Is this really 3 terms? What do you think, Kate? Right. And so will this delta here, what is that delta going to be? It's only going to be 1 if what? If I equals 1. And this is only going to exist when I equals 2. And that's only going to exist, right? So when I do this, technically speaking, when you do this sum, it gives you 9 terms, right? However, those 9 terms aren't very interesting because most of them are 0. Let me just do a quick aside here to help see where that is again. Let's say I had a dot b, okay? And I wrote this as a x hat plus y hat plus az z hat. And then I dot it. I feel like I'm hearing a bird now. Ah, okay. So if I were to do this dot product here, right, how many terms would you get from these two things here? You get 9 of them. Yeah. But would all of them exist? Yeah. What would a term like AX, X hat dotted BY, Y hat give you? Exactly. And that's what you're getting right here. So when you write this out, you're technically going to get 9 terms, but most of them vanish. In fact, you're only going to keep the terms in which I equals J. So what we're going to realize here is that while this exists, when we do the sum over J, the effect of that, so let's say I had BI delta IJ, okay? The effect of doing the sum over, in this case over I, just replaces the index I with the index J. So let me say that again, just to be clear. When you perform a sum that has a Chronicle delta, what it does is it takes this I index that they share in common and replaces it with this other index, making it a J. Carter, are you good with that? Kate, are you good with that? Okay. So now when we go back to our original problem here, we have AIBJ, Chronicle over IJ, and when we do the sum over J, it simply replaces this J with this I. Leaving us with what we could have written down in the beginning of A dot B as being AX BX plus AY BY plus AZ BZ. And really what I mean, I'm sorry, is A1 B1 plus A2 B2 plus A3 B3. Everyone following me still? So we did something we knew how to do with sums that made it look a lot more terrible, but we're going to see it's really not more terrible. All right, so what Einstein realized was that every time you do these vector sums, anytime you had a repeated index, it was accompanied by having a summation. So he realized that repeated indices only happen when you have sums. And so you'll actually see in some advanced physics books, every once in a while you'll see something like AI, or you'll see something like AI XI, and then it'll say no sum afterwards. Because it is so common to find that we actually just remove the sum. So when I say vector A, in my world, that's what I write. I don't write that summation because I know it's there. Okay? Which you might say, well, is that really helping me? And it turns out it is. That stripping away that unneeded notation makes it easier to see what you're actually looking at. Once you start writing 3, 4, 5 sums in front of something, most people's eyes start glossing over and they don't care what you're talking about anymore. But instead, we're going to say, let's just drop the summation notation because we know there's a sum. So now let's look at our dot product again, just a little bit more carefully. A dot B is AI EI dotted BJ EJ. Here we've dropped our sum, which becomes AI BJ EI dot EJ. Okay, which we now know is the Chronicle delta. So then I have AI BJ delta IJ. And now I will perform the sum over J, which replaces the J index with the I index from the Chronicle delta, which then gives you the familiar result. Is everyone following what I did? Okay. So let's imagine that you just had a matrix A. Okay. If I wanted to refer to like this component, or let's say I wanted to refer to that component, Kate, what would it be? Oh, it's row column. Okay. 3, 1. It's row, yeah. So it's A31, okay? So things that have two indices as opposed to one indice are matrices now. So then the question is, what matrix is delta ij? So take a guess. You might say, I don't even know what you're asking me, and that's fine. But what are your thoughts on what the matrix delta ij would look like? Because remember, delta ij is just a number. It is just, whatever matrix delta looks like, it's just got numbers in it. Right? So if I just say that's delta, it would be some matrix, and then if I picked, the ij component here, that'd be kind of delta ij. Okay. So what do you think the matrix form looks like, Carter? Any thoughts? It is exactly the identity matrix. It is 1 down the diagonals and 0 on the off diagonals. So it's really nothing more than the identity matrix. Okay. So delta ij is the identity matrix. So as a tool for dot products, there's really not a lot we're learning here. But the real magic of this comes in understanding cross products. Okay. So if we're now going to write out, what is A cross B going to look like? We get A cross B, and we're now going to look at the ith component of it, which sometimes we write as a new vector C and the ith component there. In case you don't know or don't remember what the cross product does, is it takes two vectors, in this case vector A and vector B, and creates a third vector, vector C. And vector C is going to be perpendicular to vector A and vector B. So what would A dot C be equal? Anybody know what A dot C equals? You might remember that the magnitude of the cross product is the magnitude of A, the magnitude of B times what? Sine or cosine? Right. Cross product. If I said A cross C, that would be a sine. But I'm asking about A dot C. So that's cosine of theta. Or sorry, C here. Okay. So what's the angle between those two vectors, A and C? And cosine of 90 is? Right. So A dot C is? Good. So that's something we're going to come back to in a minute. So if you go back and you were to write out the dot product, you might look it up in a book or something, and you would see that A cross B is A2B3 minus A3B2. Right, you guys have seen this, right? Where you go through and you write out these terms. There's 6 of them. Everyone's familiar with that, right? Kate, you're familiar with that? No, yes? Okay, so we're actually going to write it a little bit differently here as A cross B, and we're going to look at now the ith component of A cross B. Okay, we're going to add a new symbol, and this new symbol is epsilon ijk, also known as the totally antisymmetric tensor. And the meaning of that tensor is a little bit hard to think about at some point, but imagine you had a Rubik's Cube. If you wanted to pick a point on that Rubik's Cube, or a cube on that, a smaller cube on that Rubik's Cube, how many indices would you need? You would need 3, right? The first 2 components would tell you which spot on the face you go to, and the third component tells you how far back to go. Does that make sense, Kate? You follow me, Carter? Okay, think about it I'm afraid that, yeah, let's see. Imagine you wanted to pick a point on the Rubik's Cube, right? There are 3 layers of 9 cubes. So you need 2 indices to pick out which part of the face you want, and the 3rd index picks your depth. Exactly. And that's what epsilon ijk is. You know, down it's row, column, depth. Okay. So now we write it as this weird thing here. Now epsilon ijk, as it turns out, has 3 values, unlike the Chronicle delta. It is valued as 1 when the order of the indices is 1, 2, 3, or a cyclic permutation of such. So 1, 2, 3, or 2, 3, 1, or 3, 1, 2. Basically, the point is, as you read through it, are you in the same order that you were? It is equal to -1 if any of your indices are in opposite order. So 3, 2, 1, or 1, 3, 2, or 2, 1, 3. Now, this is a pretty subtle point, so I need to make sure you understand it before I move on. Do you understand how these 3 sets of numbers are different from these 3 sets of numbers? Kate, are you following me? You know what a cyclic permutation is? Basically, you can pop the 3 in front and everything slides to the right. Okay. And then the totally antisymmetric tensor is 0 anytime 2 of the indices are the same. So I is J, J is K, or I is K. Okay. Now, why is it said to be totally antisymmetric? Well, epsilon 1, 2, 3 is going to equal what? +1, right? Do you guys know what a skew symmetric matrix is? Did you learn about these in linear algebra? Okay. Let's say you had this matrix here, 1, -1. Okay. Let me actually write this one. A skew symmetric matrix is Aij is minus Aji. Okay, that's called skew symmetric. So what that means is that if you swap these 2 indices, you produce a -1. And here's an example of a skew symmetric matrix. The diagonal always has to be 0 on a skew symmetric matrix. Because A11, if it's going to equal A11, meaning you swap those 2, it has to be none. Are you following me? Skew symmetric is another way to saying antisymmetric. Kate, are you with me here? You can say no, and it's better to say no because then I say more. Okay. Right. Remember, Aij is just a number, and Aji is just a number. So let's imagine here I had A12. What does A12 equal? It equals 1, right? That's right here. A21, however, equals -1, which is minus A12. Right. So when you swap the order of the indices, it produces a -1. That's what an antisymmetric matrix means. A totally antisymmetric tensor means any 2 swaps of indices produces a -1. So if you had epsilon 1, 2, 3, and you swapped the 2 and the 3, that would give you epsilon 1, 3, 2. So epsilon 1, 2, 3 was equal to 1. Epsilon 1, 3, 2 is equal to -1. Are you guys following me there? So epsilon ijk equals negative epsilon ikj. right? Where what I've done here is I've just swapped these two indices and produced a -1. How are we doing here? Okay. Yeah. Sure. Yep. Yep. That's exactly right. Same. Yep. Same idea. Yep. Okay. So let's see how to use this. Okay. Let's go back to our cross product, A cross B sub I, which is from IJK, AJ, BK. All right. A cross B, if we look at the first component of that, would be, just use our formula, it would be epsilon 1 J and K. AJ, BK. Do you guys see how I got from here to here? Right? All I did was I made I equal to 1. Okay. Now, what do I have with the J's here? What does it mean when what do I have here and here? Somebody killing a small animal or something in the background? Okay. So what do we have here with this J and this J and this K and this K? We have two sums out front. Right? We didn't write them, but we have two of them. Kate, good. Carter, good. I'm not asking Kieran because Kieran and I already walked through this. So let's now do these sums, meaning I will do the J sum first. So the first thing you would get is J equals 1, right? But can J equal 1? No, because this would vanish. Because anytime you have a repeated index, you get 0, right? So the first term vanishes. I don't even write it. So then I get the J equals 2 term. And then I also get the J equals 3 term. Okay? Now I'll do the final sum over K. Well, K equals 1 vanishes. K equals 2 vanishes. So all I get left is K equals 3. And then the second one, I only get K equals 2. And then you go back and you say, okay, epsilon 1, 2, 3. That's positive 1. Epsilon 1, 3, 2 is negative 1. So the first component of the cross product is A2B3 minus A3B2. And if you were to look that up, you would see that that was true. That is the first component of the cross product. Which you can then subsequently compute the second and the third component of the cross product and find that to be true. Now, why is this sort of thing helpful? Well, let's imagine that you had something like DDT. There we go. So I did something like DDT of R cross S, like we're going to see in one of our homework problems. Well, technically speaking, if I were to write out what the cross product is, I'm going to get this term, a Y term, and a Z term, right? And then I'm going to take a DDT of the X term, the Y term, and the Z term. And because of the product rule, we're going to get 12 terms in our algebra. Does everybody see that? Kate, Carter, are you following that? Well, you agree that there's two terms here, right? And then there are two terms in the y and two terms in the z. Then you take a product rule derivative of those. And, well, it's even going to be more than that. It's terrible. You're going to get, what, it's like 24 terms. Right? Because you're going to get a product rule. You're going to get two terms from each of these, two terms from each of those. Oh, no, it's 12. It's 12 terms, yeah. Okay. Everyone's following me there? However, with this notation, we can do it a lot easier. We can just say ddt of r cross s of the ith component, which becomes ddt epsilon ijk rj sk, which then this becomes a derivative of three quantities. However, this term is just 0, 1, or negative 1, so it's constant. Bring it outside the derivative. And now you have this derivative here, which is much more reasonable to handle. Are you guys following that at all? Like, this product rule is going to be a lot easier to do, right? That's going to be epsilon ijk dr dt sub j times sk plus epsilon ijk rj dfk dt, right? And that's a much simpler thing to begin evaluating. All right. Let's go back now and look at that one statement I made about the cross product and the dot product. So let's imagine you had C being defined as A cross B. Okay. We know that A dot C should be what? It should be 0. Well, let's see from this notation what we get. Well, A dot C is going to be what in this notation? It's going to be AI, right? CI, right? Which is going to be AI epsilon ijk AJ BK, right? Because CI is epsilon ijk AJ BK. Right? This is just the same definition we used from above. We plug it in here. Well, so now we have epsilon ijk AI AJ BK. Now, why am I able to swap the order of A and epsilon? Kieran, you should know this one. Why can I swap those orders? They're all commuting numbers. Right. Right. So now let me ask you this question. Are you free to swap AI and AJ's order? Well, you should stick with what you just said. They're just numbers. Right. So then I could write this as epsilon ijk AJ AI BK. Okay? Well, if I want to keep it looking like this one, I then have to swap the order of those two indices. And what do you get when you swap the I and the J? Right, so now you get negative epsilon j I k AJ, AI, BK. Now, do the I and the J and the K mean anything? They don't. They're what's called dummy indices of summation. So I could, if I wanted, let J become M and let I become N, just to make my life a little simpler. And now I get M, N, K, AM, AN, BK. Now, why did I do that? Because I wanted to help us see that this line and this line are the same. Do you guys see that? It's a sum here, 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 and a sum here. Barring the minus sign, they're the same. So what we've just shown is that A dot C equals negative A dot C. And the only way that's possible is if A dot C is 0. Now, I'm not expecting you to be able to like turn the video off and reproduce this right away. That's what homework's for. But that's some of the power you're going to be getting out of using this notation. Okay. Any other questions for now?